So a very good evening to you all. Welcome to Institute of Engineers Sri Lanka Western Australia Chapter's second lecture of its 2001 lecture series. Tonight's presentation is organized by our Electrical Engineering Subcommittee. My name is Anuradha Vijayasinghe. I'm the Secretary of Iesl Wa Chapter, and I will be your moderator tonight. So before we begin, a few formalities and online etiquette I would like to just go through before we start. The lecture is about maximum an hour. I will give our presenter a notice at the 45-minute mark. You will notice that your microphones are set to mute, but I would also like to put your mic into mute as well on your end. And there will be a question and answer session at the end of the presentation. So without further ado, I would like to invite the head of our electrical engineering subcommittee, Dr. Sumedha Rajakaruna, a fellow professor from Curtin University, to introduce our speaker tonight. Thanks. Over to you, Sumedha.
Thanks, Anu. Thanks for that opportunity. It's my pleasure to introduce Professor Arindam Ghosh, one of my colleagues at Curtin University. It's a rare opportunity for us to get his kind acceptance of this speech. So let me give the brief biography of the speaker, Professor Ghosh. Professor Ghosh obtained his Bachelor of Engineering and Master of Engineering degrees in Electrical Engineering from Bengal Engineering College, now known as the Indian Institute of Engineering, Science and Technology. He then received his PhD in Electrical Engineering from University of Calgary, Canada, where he spent 6 months as a postdoctoral research fellow as well. He worked 1 year in Tata Electric Company from 1984 to 85, and then he joined Indian Institute of Technology, Kanpur, IIT Kanpur in 1985 as an assistant professor, and he became a full professor in 1991. In 2006, he joined Queensland University of Technology in Australia as a research capacity building professor in power engineering. From December 2013, he is with Curtin University in Western Australia, where he is a professor in research academic capacity. He has obtained 11 Australian Research Council grants and others with a grant income of around $8.5 million. He has supervised over 80 higher degrees by research, that is master's and PhD students. He has over 450 publications, including books, book chapters, peer-reviewed journals, and conference papers. His research is mostly focused in control of power systems and power electronics devices, particularly power electronics to power systems, including microgrids. He was a Fulbright Scholar in 2003, and he has been elected Fellow of Institute of Engineers India in 2004, Fellow of Indian Academy of Engineering in 2005, Fellow of Institute of Electrical and Electronics Engineers, that is IEEE Fellow in 2006. He is an IEEE Power and Energy Society Distinguished Lecturer since 2014. He is an IEEE Power and Energy Society Narihingorani Custom Power Award winner in 2019. So this last one is a global award that he received recently. So it's my greatest pleasure to introduce Professor Ghosh. Without further ado, I invite Professor Ghosh to deliver the talk, please.
Okay, thank you, Sumedha. Shall I start now?
Yes, please.
Can you guys hear me?
Yeah, we can hear you.
I think
Yes,
most of
we can hear you.
Yeah.
Okay,
They will
thank
be
you.
on mute.
Okay, all right, thanks. Okay, so thank you, Sumedha, for the introduction. And I told you that the introduction got to be shorter than the talk itself. But anyway, so let me start. So my talk is microgrid current status and future outlook. And if you see, I have captured that Iesl logo here beautifully. Okay. All right. So, and so the thing is, what is a microgrid? All right. So this is the question. I mean, a lot of people have heard the term microgrid, etc. And question is, what is a microgrid? So basically, this was proposed by the Consortium of Electric Reliability Technology Solutions, that's called CERTS in California, and it's around early 2000. It's basically an aggregation of electrical loads and generation. And if you are looking from the utility point of view, then a microgrid is an electrical load that can be controlled in magnitude. So usually your electrical load cannot be directly controlled, but this one is a load, aggregated load. It can be constant. It could increase in night when the electricity is cheaper. It could be zero during the time of stress. That means when your system is stressed, the microgrid will not absorb any power, or it can even supply power to the grid when the grid is under stress. So this is the basic thing of a microgrid. We'll go through it slowly and show you what it means. Now, if you look at the conceptual diagram of a microgrid, this is it. So you see, this is a microgrid. You can have generating wind power plants. You can have battery energy storage. You can have a gas plant. You can have solar plant. You can have factories. You can have houses with electric vehicles. You can have control centers. You have public facilities, city and buildings, and you can have diesel generators. Remember, even though we see diesel generators and gas power plants here, people are slowly going to phase out these things because of the concerns about climate change and all that. But for the time being, they are still there, and they will be there for some more time before we can actually get rid of them. Now, there is a caveat about microgrid definition. The thing is, you will hear people saying, oh, we have got a microgrid. We are running a microgrid. Actually, they don't really know what they're talking about. So I must, at the beginning, specify what is the definition. I mean, if you put a, say, rooftop PV and with a battery, and you are connected to, say, Western Power System or whatever system, whatever the utility that supplies your home, and you say, I have a microgrid, then that's rubbish. That's actually not a microgrid. And this is a common mistake made by many people saying that we have a microgrid. So the Navigant research, they have defined it in line of CERT's microgrid definition. It's a distribution network that incorporates a variety of possible distributed energy resources. Distributed energy resources will come to that. That can be optimized and aggregated into a single system that can balance the loads and generation with or without energy storage, and is capable of islanding, whether connected or not connected to a traditional utility power. Capable of islanding. Okay, so this is the basic definition of this. So you can operate in grid connected mode, or if you, I will come to that in the next slide. So if you look at the CERT's microgrid concept, so these are, of course, different types of load. You have sensitive loads, say, for example, a hospital or something. So this load has to be supplied. Then you have adjustable loads. That loads you can actually adjust their magnitude. And then you have sheddable loads. So when you are under system stress, you can actually shed them. And there are various these things like radiators, PV panel, etc., hot water system. So they are actually indicated in this diagram. And if you look at this microgrid is connected to the utility at point of common coupling. We call it PCC. And usually, according to such definition, you will be connected to this, the utility will be connected to the microgrid at one point of common coupling. The basic reason is that suppose there is another connection here, or even say here, and when you want to island, you have to disconnect both the switches. Because if you disconnect it here and it's still connected here, so the whole thing is still connected to the utility. So according to this, you have a disconnection at this point. Okay. So now I will go to a bit of history actually. That is world's first microgrid installation. And you guys, I mean, those who are electrical engineers amongst you, we will be able to see this diagram and we'll be able to recall what this is. All right. This is actually the first power system in the world, the power system in the world. This is the Pearl Street Station, Lower Manhattan, which was set up by Thomas Edison, and he wanted to just supply customers enough power to actually light 100 watt bulbs. Okay, so he actually did a lot of innovations for that time. So he had coal fire steam engines that drove DC 6 jumbo generators. He used to call, because of their size, he used to call them jumbo generators. Each generator produced about 100 kilowatt power, and that could supply about 1,200 lamps, 1,200 lamps. And what was this is that he used the generator output exhaust for heating as well. So that's called combined heat and power, CHP. And he even thought of that at that time. The project had about 80,000 feet of underground conductors in manhole and conduit configuration. So they will pass through manhole and then through conduit. The original system was 110 volt DC, but then he realized the voltage drop is too much. So it was changed to 3-wire 220 volt system. So you will have 110, 0, minus 110. So you could use both sides of that. And these resulted in saving of copper conductors. So there was, oh, shut up. Where is it? Idiot. Anyway, so that's saving of copper conductor. This system started with 400 lamps for 90 customers, and within a year grew up to 10,000 lamps, serving about 513 customers a year. Unfortunately, despite all this, Edison's DC power system died. There was a long war between Edison on one side and Westinghouse, George Westinghouse and Nikola Tesla on the other side. And Tesla, the AC won simply because of the reason Tesla realized if you use transformers, and then you can actually change the voltage. You can make the voltage go up, you can bring the voltage down, etc., etc. And thereby actually then AC has become the de facto standard simply because of transformers, simply. So you could actually counter the voltage drop, which you could counter here, because at that time there were no DC-DC converters, which we'll be talking about a little bit at the end. So this is the reason. So Edison system died, but if you look at the historical perspective, that is the first microgrid, really, because it was only connected to the Manhattan system and not anywhere else. Now, if you look at the global investment, renewable power and fuels in 2018 totaled about close to 300 billion US dollars. It actually, including if you include the hydropower plants larger than 50 megawatt, even though it was an 11% decrease in the previous year, but in a fifth year of the row, the investment increased $230 billion mark. However, we must remember that the decline in investors reflects to some extent the falling cost of renewable. Now, I was reading a report about the investment in microgrid. Of course, like everything else, it got a hit recently because of COVID situation, but it's still a lot of investment. We'll be talking about a few of them. Now, if you look at the microgrid components, then microgrid is supplied by distributed generators. It's called distributed generators because they are placed all through the distribution system. So they are called, and they are distributed. So they are called distributed generators. And when you add the battery energy sources with them, they call distributed energy resources. But you can talk about them interchangeably. And as I mentioned, it can operate either in grid connected or in islanded mode. When islanding occurs, when the microgrid is disconnected from the grid, in an islanding mode, all the DGs need to supply the loads, and following this, load shedding may be required. So if we look at this components of microgrid, so this is wind, battery. This is micro turbine. They actually operate in natural gas, and they operate at a very high frequency. So you need a converter system to bring the frequency down. Then this is fuel cell. And this is diesel engine. So this is, unfortunately, they will still be there for some more time. And this is battery bank. So all these components, most of them are renewables or can run on renewable. Even biodiesel, if you have enough biodiesel, then you can convert this. Then you can get everything here to run on diesel. And fuel cell, if they are hydrogen fuel cell, then of course it's all renewable. So these are the summary. Now, what are the benefits? Okay, so now I will talk about the benefits of microgrid, and then I will show you one application where microgrid, how it served when it was required to serve or something. Okay, microgrid benefits, it can improve the reliability of power supply, possibly at a lower cost. Obviously, once this is established, most of these through renewable sources, all you have is to generate power and maintain some rudimentary maintenance. You have no fuel cost. And the technology can be effectively used for combined heat and power. In fact, all these combined cycle gas turbines that is used for even say micro turbine, etc. So they use combined heat and power, which is probably not a big deal in a country like Australia or Sri Lanka, but it's a big deal if you have ever lived in Canada. So where during winter you need as much heat as possible. It will reduce the transmission power loss. It will reduce the environmental impact. You have energy diversification, that you are not only relying on coal or say hydro or whatever. It can support the network voltages. So if you have when you have a voltage collapse problem, you can avoid it. And it is suitable for off-grid and remote area applications. In fact, this is one of the main developments currently. So let's look at microgrid in Japan. So in 2003, almost 20 years back, the Japanese government, they had this new energy technology and industrial technology development organization, or NEDO. They said we will put up 4 microgrids, I think 4. 4, yeah. The objectives were to demonstrate the working principle under high penetration of renewables, islanding, and power quality. The original objective was none of the project included system resilience. We'll talk about that in a short while. Okay. One of these 4 was Sendai Microgrid project in Tohoku Fukushima University campus. Now, this is the schematic diagram of Sendai Microgrid. You can say it had photovoltaic gas, fuel cell, DVR, another DVR, building 1 integrated back-to-back voltage source converters, all for test equipment, so beautifully. Now, unfortunately, this one was located near Fukushima. So, you look at Fukushima in 2011, probably January 2011. This is what you see here. The place, Sendai, this is what you see after the water receded. However, the Sendai, if you can see in the previous slide, was severely affected. Okay, but the microgrid was well prepared for earthquakes in many ways. Okay, it didn't have like the piped gas supply that we have in our home. If there is an earthquake or something, the whole thing will rupture. But this was not the same gas supply as the natural gas supply, but it had a hardened structure, and it was much deeper. It was the pipeline went much deeper in the earth. I think it was placed some 10 meters or something below or something. And when the earthquake occurred, the local utility stopped supplying power to the area surrounding the microgrid, resulting almost in a 3-day outage. Nevertheless, the microgrid was able to continuously supply power for some critical loads. Of course, they switched off all non-essential loads. So they supplied some critical loads within the campus and provided full heat and power service for almost 2.5 days of these 3. And then, of course, the gas supply and the battery backup, everything ran out. So they had to stop. So when people looked at this, after all these happened, it took people to realize what happened it took them about a year or 2 to realize. And they realized, oh, this is a very great thing for resilience. I mean, it's something, there is a outage, I mean something, then this can be our savior in many ways. And even you can cold start the AC power system from these. I mean, you can start synchronizing based on a microgrid. So there are a lot of improvements or that are people are talking about these days. Now, if you see the microgrid installations, they are various places, municipalities, ports, military. And if you look at the military installation, the main reason for this is that if something happens, if there is a foreign threat, they want to take your installation out of the main grid, because if they hack into your command and control center, you are gone. So whereas if the command and control center is supplied by a microgrid, which has no outside connection, you cannot hack into it, and then your defense mechanism or defense equipment are all safe. Similarly, correctional facilities, which are called prisons. So if there is a power failure in the prison, there will be riots. So they want to put a microgrid there. And hospitals for obvious reason. And there are several university campuses, and that's also obvious reason. They want to see how they function because they are interested in research and improving the standards. So several university campuses, especially in the US, they have microgrids. And you can see there are, I mean, I'm not going through them, but there are diverse facilities and aims are also diverse. Like the municipality microgrid, aim of this is not same as the port microgrid. So if you look at the growth, high growth you can see is in Africa. Medium growth is in the North America, India, I mean, Iran, all the China, all the way down to Australia, Sri Lanka, sorry, New Zealand, of course, India, Sri Lanka here, and others are there. And low growth, very low growth, is in South America, and I don't know, for some reason, Europe. The reason for Europe low growth, I suppose, is that they have lots of wind. I mean, here along this coastal line, they have lots and lots and lots and lots of wind. So if you have wind and they have a massive mega grid which is connected here, so they probably don't need that many small and medium scaled microgrid. Now, if you look at the types, revenue share in 2019, these is commercial facility, and you can see a big chunk is remote off-grid communities. Okay, now if you look at Australia, Western Australia, we have so many off-grid communities where they can be supplied to remote area. I come from India. I know there is a lot of possibility where you can have you can have small hydro and then you can set up a microgrid up in the mountain. I am not very sure of Sri Lanka, unfortunately, because I think Sri Lanka is a very small country, so there should be, they're probably remote areas are limited. Anyway, so these are institutions and other sites, and these are others. Now, remote area microgrids. So that is what I said is if you look at the previous figure, this is the maximum development is taking place here. So remote area, one project was signed in 2019 for Myanmar. And then I put 3 question marks. It can be question mark recurring because you don't know what is going to happen in Myanmar. So let's not bother with it. Then Maharashtra Energy Development Agency allocated about 6.1 million Indian rupees for not much, 29.4 kilowatt for 3 remote villages. Canada approved 300 microgrid remote off-grid communities because Canada has off-grid communities which are, I mean, only few people like here, and but they are remote. Tata Power is setting up in microgrids in Bihar, India. Tesla has over 200,000 operational microgrids containing solar inverters and batteries. Tesla, they're promoting their batteries, and they have they actually also bought something called sun power or solar power or something, and they are actually putting up these microgrids. They have about 120 operational microgrids. This is probably when it develops, it will probably be the largest microgrid test site. This is an island called Palau in Pacific Ocean. It'll be nice to visit them at that island, I suppose. Go there, relax, drink coconut water, and so on, and gorgeous weather, gorgeous sun, etc. But this microgrid will be diesel, solar, and battery. As I said, you see this island now only depends on diesel, which has got apart from industrial pollution or the pollution, but that pollution doesn't probably affect the island more than anything because it's a small island and it will just blow away. But it affects the global climate. But what happens is when you put a solar and battery, so they have a 35 megawatt of solar and 45 megawatt hour battery for a power capacity of 100 megawatt. So what will happen is that when you replace this by diesel by these, what will happen is the import. I mean, diesel is very expensive in that because you don't have diesel or you don't have a refinery, so you have to bring diesel from outside, and it's probably a remote island. So to get the diesel there will probably cost them something like $5, $6, $7 a liter. So they will be able to avoid that. So if you look at this, I mean, then this remote area microgrid can have different perspective, different everything. Okay, now I have to go a little faster. Okay, now if you look at this is called grid connected microgrid. You have a substation, this is a transformer, and this is the switch at point of common coupling. And you have different devices like diesel, microturbines, solar, etc. And you have an energy management unit. Okay. Then the supply sets the frequency. So if your system is very big, this is insignificant compared to this. So the supply will set the frequency, and the DGs, means these things, or DERs, will control the local voltages and reactive power. So you are not going to do anything to the frequency, but you are going to control the reactive power and the local voltage. Now, when this switch opens, okay, so you will say it's an islanded operation because this is it. I mean, when the switch opens, suppose this thing is totally cut off, so then you have these loads and all that. They have to be managed by all these DERs that you have here. So that is called an islanded operation because you are now an island. So basic purpose is that when a synchronous generator operates in a steady state, is suddenly loaded, it slows down, resulting in momentary drop in frequency. Also, the bus voltage drops when a large amount of reactive power is drawn from it. So basically what we will do, use these concepts of what is called a droop control. A droop control is what you see, you set a frequency which is in proportional to the active power, and you set the voltage magnitude which is proportional, sorry, oops, this is wrong. This is reactive power. This should be Q. So you have a voltage magnitude which is proportional to reactive power. That is Q max minus Q. So let's look at this. So how does it operate? Suppose these are two generators, and they are operating at 50 hertz, and suddenly your power requirement increases. So what happens is that, as I mentioned, that when the power requirement increases, the frequency actually drops. So when the frequency drops here and here, I mean, if this one supplies this additional amount of power, this much, and this one supplies this much additional amount of power, then the frequency of the entire system will remain constant. And that's the basic principle of droop control. You cannot, in a system, you cannot operate one generator at 50 hertz, another generator at 50.1 hertz. Your system will have large oscillations and damage. So that's not possible. So that's the principle of droop control. You can also show about the voltage and reactive power about that as well. So the transition from islanded mode and grid connected mode is generally planned. So suppose there is a fault on the other side. So what happens is that you just go into islanded mode, and then when the islanded mode finish, you want to go back to grid connected, to grid tied mode. So here, this is a very challenging problem. It's not that easy. Anyway, so but the basic thing is that when you connect an AC source with another AC source, you have to maintain that the phase sequence is same, the voltage is same, and the frequency is same. So direction of rotation same, frequency is same, and the voltage is same. And then you have to connect. I mean, we used to have a lot of fun trying to do this synchronization when I was teaching in IIT Kanpur. We used to have all these experiments, and we'll every time that was a challenge for every batch which did this experiment. It was a challenge, and I was very good at showing them how to do it. So anyway, so that is called synchronization. So you need, there is no, you have to be automatic. It has to be automatic. So you cannot expect somebody will be there to do a resynchronization all the time. So actually, then comes the question when we are talking about microgrid. Now we are seeing a lot of involvement in this. The power electronic prices are coming down. The switching frequency is going up. The communication infrastructure is becoming better. And when you have all these, I mean, and the prices, say, for example, the prices of solar or wind or inverter, when they hit the floor, what you will see is that why the hell should I pay money to Western Power or wherever, so that if I can put up a solar PV and a battery in my house, then I will disconnect from them. Okay, so that's not going to happen soon, but it will eventually. There is a lot of thought that we might go up the pole or up the wire. So this is called smart microgrid or hybrid microgrid cluster. So what happens is that, see, you have all these microgrids, and this is one power exchange highway. And these microgrids are connected to each other only through this power exchange highway. And these are isolators. Isolators can be back-to-back converters, or it can be some other kind of switch, which will connect this microgrid with this microgrid as and when they are required. And also the central station will be here, and this is central generation, transmission, distribution, etc. And this is also connected to the power exchange highway. So this hybrid microgrid cluster will be, as I mentioned, all of them will, the power exchange is only through the highway. So everybody will have to come to the highway to exchange power. The cluster will coexist with the existing power infrastructure for the time being. However, when you have sufficient number, you can say, okay, get rid of the central generator, and we will have this. Here, if each microgrid helps each other, then we don't need really. See, for example, this microgrid may have a power shortfall where the other microgrids will supply. That's one structure. The other is called network microgrid, which is like this. You have a distribution system, and there are several microgrids, and they can be connected to this system here, or they can be connected together along with this. So this is called network microgrid. So if you look at this network microgrid, and then there are different structures. So this is microgrid connected. This is microgrid is connected in series. Two microgrids are connected in series with the main grid here. This is two microgrids are connected in parallel with the main grid, but they are also connected in series. And then here is two microgrids are connected between two feeders, and they are also connected here. So there are lots of people are talking about this, and this actually is also, if you want to do, I mean, what this idea here is quite revolutionary. This is the best idea. However, for the time being, when you want to do retrofitting of the existing system, this is the type that you are going to see. And now I am almost coming closer to this thing. I'm just talking about Edison's revenge. A large majority of electrical loads, like LED lighting, adjustable peak drive, electric vehicles, computing, etc., they need DC. At the same time, many DERs like PV, batteries, fuel cell produce DC voltage. Even you can have a wind with DC generators, what you are doing is you are generating DC, and then you are converting, inverting it into AC for grid connection. So, and that is obviously when you do that, you are incurring losses for this. Okay, so that's no good. So that's why the use of DC grid is getting traction, as this reduces the conversion losses. And voltage transformation, which was unfortunately not there during Edison's time, they can be accomplished through DC-DC converters, which have more than 95% efficiency. So the losses there are very small. Now, if you look at this, this is a DC microgrid. What happens is this is the utility, distribution, then AC to DC converters, and then you have wind turbines, again AC to DC, could be DC-DC, PVs, electric vehicles. You can have an AC load, which will convert this back into this, and so on. And you have household items, etc. and you can have storage like flywheel, battery, etc. So just couple of more slides. What is the advantage of DC? There is no skin effect. The current can flow through the entire cable, not only the outer edges. This will minimize the loss. There is no need for synchronization. And as I mentioned, you don't have to, you can just connect. And the beauty of DC is that if you just adjust the voltage, the current can flow from higher potential to lower potential. So there is no reactive power control. There is no angle control, nothing. However, AC system scores in one aspect. The protection of AC systems operates on the principle of natural zero crossing of the current. Means when there is a fault, you want to open and your current is still sinusoidal. So you look at the natural zero crossing of the current and open your breaker at that time. So there is still flashover, but you still have a very good chance of extinguishing the fault current while you switch off, I mean, while you separate at the natural zero crossing. However, in a DC system, there is no natural zero crossing, so the protection is more challenging, and new products and standards will be required for large scale uptake. Means I have seen at one time there were DC used in Calcutta, and there were AC as well as DC. So you could buy lots of things which were DC. Now that has been discontinued. Now we have to get back. We have to make appliances that are DC, etc., etc., etc. And the DC has the problem of grounding and corrosion. If you look at this, the main use of DC is marine application, actually, really. So if you look at the ship, so basically you have a DC motor. Sometimes they have a diesel generator, 2 diesel generators, which are turning the screws as well. And these then will be converted into AC, DC, and they will be having batteries and the other service load and shipboard energy management, etc. So basically, even if you look at this big cruise ship, 17-storied cruise ship, etc., most of them supply through DC, several circuit DC power, which the power is generated by these big, monstrous screws, generators, which will turn the screws as well. So if we conclude now, microgrid research and development projects are gaining momentum worldwide. The future of low and medium voltage distribution grid in microgrid clusters and network microgrid. In these streams, microgrids can support each other and the utility system. And as I said, moreover, black start following a catastrophic failure is one of the benefits of network microgrid. Unfortunately, the R&D scope, even though it's enormous, it's not that good in this country. Okay, so oops. So thank you. And if you have questions, then
Thank you.
Shall I stop
you, Professor Ghosh. I will now open the forum for any question and answer session.
So I'm sharing or what? Yeah, I think
sorry?
that is. No, I have just stopped sharing.
Right. Yes. Okay. So if anyone has any questions, please remember to unmute your mic and also let us know your name and your engineering stream for the benefit of the presenter and the rest of the audience. Thank you. No questions at this stage.
May I ask a question, Anu? Okay, my name is Sumedha from electrical engineering stream. So my question to Professor Ghosh is that grid-connected microgrids, we don't see much of development in that area, and most of those implemented ones are off-grid type and very specific purposes. But when it comes to virtual power plants, there's a lot of movement happening in that area. So what is the similarity and what's the difference between the virtual power plant and the grid connected microgrid?
So that's a very good question, actually. Okay, very good question. But grid connected microgrid is actually, I know why it is not happening. Because, see, for example, suppose all of us we live, say, side by side in a community. Suppose, let's say all of us live side by side in a community. All of us, we have decided, okay, now we'll put a solar PV in our roof and we'll put a battery. Like, if you go to Alkimos Beach, they had some 3 million arena grant where every house there. It's a beautiful area, but it's a bit too far. Otherwise, I would have gone there. It's a bit too far. I think it is north of a city, 40 kilometers or something north of city, and it's by the side of the sea. So beautiful. Anyway, so what they do is that every house will have a PV, and they have a huge, monstrous battery system. I think that is 3 megawatt hour battery system. So that is actually, it's not really a microgrid. So what is it? It's not a microgrid, but it's a combination of solar with battery. You can have an individual battery at your home with your PV, or you can have such kind of arrangement. So that is why you don't see grid connected microgrid. Whereas BPP is nothing, it's just a program. Okay. Now suppose all of us have PVs plus batteries, and some company is saying that, okay, what I will do, I will control your whole thing, the entire thing. I will put you all these softwares. I will give you some microcontrollers, which I will put you to your devices, and I will control the whole thing through my software. And then, suppose you are seeing that you are getting a profit of, say, 20 cents a day. They will say, okay, I will give you a profit of, say, 30 cents a day or something like that. And you will get your money back within, say, 2 years, whereas here you are thinking that I will get my money back in 5 years. So what they do is they coordinate the whole thing together and supply you and supply the rest, sell the rest to the outside people. So that's how BPP operates. So they don't actually they don't build any infrastructure there. Okay. So they come, use your infrastructure, put their software and run. Whereas a microgrid, you have to put your own infrastructure, whether it is grid connected. As I said, off-grid, of course, it makes more sense now, but at a later stage, these network microgrids or clusters will come.
Okay, thank you very much for the answer.
Professor Ghosh.
Yeah.
I'm Tissa Vijayasinghe. I have been working with the power authorities for a long time. And especially in Western Australia, where you have vast remote areas and vast pockets of villages, you can say, or load centers. My question is twofold. One is, can we have clusters of self-sufficient small microgrids which are interconnected in turn and forming a part of separate big grid? And second part of the question is, how far Western Australian government has ventured into this idea to power their remote villages?
Okay. All right. So again, very interesting question in the sense that some of it is, of course, political. And Sumedha knows me. I am not afraid of making bold statements, whether it's political or not. So the first part is that yes or no. That you can actually put up small microgrids. Obviously, that is yes. And no means, can you form them cluster? That probably will not make sense. Suppose if you look at Western Australia, the state of Western Australia is probably close to the size of India. You know, it's so big, so big. Whereas the population of Western Australia is about 3 million, population of India is 1.3 billion. Okay, so if you look at a village here where probably 50 people live, the next village there is 50 kilometers away. So if you want to form a cluster, you have to join them through 50-kilometer line. Okay, which will not make sense. Okay, that's the big problem. But if those villages are like in India or Sri Lanka, side by side, just 1 kilometer away or 2 kilometers away, then that's possible. Okay.
Right.
The other thing that is, yeah, Western Australia government, of course, now because of this virus, everything has taken a beating actually. But Western Australian government, they came up with a white paper about microgrid, and I had that report. I mean, this report is, I don't know, this is not technical. Okay, I think they all bureaucrats who write these reports and all that. So there was some this thing, and I thought there will be some movement, but there was no movement. And then the virus came, or COVID came, and everything is now, God knows where they are. People are just trying to survive. But yes, for Western Australia, for remote areas, that's the only way to go. And actually, in fact, in NT, Northern Territories, there is a big power plant, microgrid, which has been set up by ABB. In fact, one of former students was a manager there. So, and have you heard the green hydrogen development project somewhere in north by the which will be done by FMG Forest, Andy Forest, and what they want to do is they want to use the renewable energy to produce hydrogen, then mix it, convert it into methane or something, and then ship it to Japan and elsewhere, where they will be hydrogen will be recovered back to use it for cars, automotive, or power generation, etc. So that's a big project. In fact, there is also a project where that part of the power which is generated through solar and wind, they will be transmitted by undersea to Indonesia, and from there on to Singapore, which is viable because that distance, if you look at it, it's not that much.
Thank you, Professor, for the answer. And another small question. Is your presentation could be made available to us?
Yeah, sure. Not a problem.
Okay.
I will email it to Sumedha.
Thank you so much.
Just on that note, I also found out that this presentation will be available online through YouTube. So if anyone needs the link, I can send it out after the presentation, or once it's uploaded and after the presentation. Any other questions?
Anu, there's a hand raised.
I Sorry, I saw that. So what do I do here now? Do I invite or?
I will ask to unmute.
Okay.
Ask the person to unmute
Yeah,
and ask the
he's
question.
unmuted now.
I did send a question to that person privately asking if they have a question. They haven't responded to me, so I wasn't sure.
Yeah,
my name is Harit Kulasingh. I'm from Scotland. I'm electrical engineer, and I was involved in designing of power system analysis of submarine systems. And I thought asking Professor Ghosh whether he thinks that a submarine electrical system can be defined as a microgrid.
It is indeed. See, basically, when I was in Brisbane, we had a project with DRDO about their submarine power systems. Of course, you know this. This is a obviously what is it called? Where I couldn't declare anything. What is it? National Secrecy Act or whatever. But what we realized, what we had to do is we have to give them a model where they will be able to simulate this system, which is called hardware in the loop. So we had RTDS there, and we were giving them how to incorporate their converters and everything in RTDS, so that they want to support they want to do their own studies themselves. Of course, they won't allow us to do that, which makes sense, of course, because that's the national secret. Anybody they know what is the power system like, they can actually do a lot of damage in there. So yes, of course, that's a microgrid, and because diesel electric submarines, which is what they are doing in Australia. Whatever class they are called, I don't know. They have different classes, etc. Collins class or what? I don't know. Of course, they're not nuclear, but they are diesel electric, and the power system is DC. I don't know about nuclear subs. I think nuclear sub has enormous power, so they can do anything.
Yeah, I mean, obviously, I'm also has to respect the national, secrets act in the UK. However, and I was just thinking that the analysis we did when you reverse power, when the nuclear generation stops and the battery comes in, it's normally through a motor generator set, and the power reversal, because the direction of the power reverses. I think if some of that knowledge, obviously, there are some is secret, but some of that knowledge could be brought in to microgrids, outside the naval environment. There could be a lot of learning transferred.
True, but see, basically, I don't know about nuclear subs, but basically, if you look at the cruise business or cruise ships and all that, the recreation ones, they actually use microgrids. In fact, one of the large manufacturers of cruise ships, which is Mitsubishi Heavy Industries or MHI, and we have been talking to them for some time for a project on DC microgrid, but unfortunately, again, this virus has, so Japan is in bad shape, we are in bad shape, everybody else in bad shape, cruise industry is totally gone. So I don't think we are going to get any projects in any time soon. So where these can be studied really. And the submarine is, possibly those who are have expertise in marine application, they can say what knowledge you can actually bring in to microgrid research and development.
Thank you very much.
Thank you, Harry. Any other questions? If there are no more questions, Sumedha, shall we wrap it up?
Yes, Anu, I think it's probably time to wrap it up.
Okay, so I would like to then invite Iesl Wa. He is the president of Iesl Wa to conclude tonight's this evening's presentation. Thanks.
Thank you very much, Anuradha. First of all, Professor Ghosh, thank you so much for your time, and thank you very much for a very informative presentation. Especially it is very, very useful for electrical engineers like me. And I know your time is so valuable, especially these days. And I want to extend our sincere thanks on behalf of the members of the IESL Western Australia chapter, and also on behalf of all participants that took part today, and also from IESL main body. On their behalf, I wish to extend my sincere thanks to you, and also to Sumedha for organizing this, organizing and proposing this wonderful lecture, which is very appropriate for electrical engineering subgroup. Please accept my sincere thanks for you also, Sumedha. Then also our participants, which gives a big support to us to continue with our program. And not least, last but least, I want to thank Chamila from IESL base camp for his lavish support whenever we make requests regarding these webinars. And without any hesitation, he always come forward to go out of the way and help us. So thank you very much all. And with that note, I would like to conclude this session. And thanks all. Good night and safe time. Thank you.